Hello students, in this video we'll prove that Liouville's number is a transcendental number. So Liouville's number is L, and L is 10 to the negative 1 factorial plus 10 to the negative 2 factorial plus 10 to the negative 3 factorial plus 10 to the negative 4 factorial plus the general pattern is 10 to the negative n factorial on forever. So it's this infinite sum, and the decimal expansion looks like what? The decimal expansion of this number looks like what? You have a 0.1, because that's a 1/10. Then you have 10 to the negative 2, that's a 100th over there, because 2 factorial is 2, so I have a 1 to the 100th. And then that's going to be a 1 over 3 factorial is going to be a 6, so I have it in the 6th spot. So I have the 6th spot has a 1, 1, 2, 3, 4. And I have to go way more zeros down. Many more zeros down to all the way to the 24th spot. In the 24th spot, I'm going to have a 1 over here. Then the next one's going to be the 120th spot. So all these are zeros. So zeros over here, then a 0, then a 0, even more zeros. In fact, how many zeros? Up to the 120th spot, then a 1. So there's ones that keep getting pushed further and further and further down the decimal expansion. So this is this is a number, it's a real number, and I want to show this number is transcendental. It's not the solution of any polynomial equation with integer coefficients. So we claim L is a transcendental number. Okay? In other words, it's not the solution of a polynomial equation. There's no polynomial equation with integer coefficients. Okay? All right, so let's prove this. So we're going to use a previous video. In a previous video, we showed the following. We proved previously, so previously we had this Liouville result, previously. Liouville's theorem states if R is the root of an x to the n all the way down to a0 is equal to 0 with the aj integer coefficients, then either R is p over q, then there is a constant, right? There exists a c greater than 0. There's a positive constant. Either R is p over q, or R minus p over q is bigger than or equal to c over q to the power n. That's Liouville's theorem on the approximation of these sorts of numbers. So let's suppose we could actually find a polynomial with integer coefficients. So suppose that this polynomial p capital of x is a n x to the n all the way down to a0 with integer coefficients with a0, a1, an, and z, and p of this Liouville number is equal to 0, right? Okay, so what do we know? So either this number is going to be a rational number, right, which it's clearly not, because we can easily prove this number is not irrational because there's no distinct, it goes on forever, there's no pattern, right? And so I can therefore say that for any so what I can do now is I can try to approximate this with what? With a sequence. And so what I'm going to do now is I'm going to consider a special sequence. I'm going to look at the numbers pm, and these pm are going to be 10 to the m factorial, and then 10 to the negative 1 factorial plus 10 to the negative 2 factorial. It's just going to be the partial sum of this series up to level m, and I'm going to multiply by 10 to the negative m. So this is clearly going to be a positive integer, right? And then qm is just going to be 10 to the m factorial. That's also a positive integer, right? And what can I say? I know that since this L is not a rational number, I know that I can bound this. I know that L minus pm over qm, and of course L is not equal to this number over here. So so the ratio of pm and qm clearly stops at 10 to the negative m, but L goes on forever. So pm over qm is not equal to L. It's going to be bigger than or equal to a constant over q m to the power n, where n is the degree of this polynomial over here, right? So that's our estimate that we get for these things. of course, what can we say now? Let's estimate the difference of L and Pm minus Qm. So what is that difference over there? So that difference, this difference over here, so C over, now Qm is going to be 10 to the m factorial raised to the n is less than or equal to, well, it's just going to be the sum. J goes from m plus 1 to infinity of 10 to the negative j factorial, okay? Now, each of these terms over here is going to have, I have an m plus 1 factorial, an m plus 2 factorial, m plus 3 factorial, m plus 4 factorial. They all have an m plus 1 factorial in it, so I'm going to pull out a 10 to the negative m plus 1 factorial out of that sum. And then all the other terms are going to be a what? The first term is going to be a 1, the next term is going to be a 1 over 10 to the negative m minus 2, et cetera, et cetera, et cetera, et cetera. For m large, I know that all those terms are no more than what? All those terms are bounded by a geometric progression. So the tail of that series, once I pull out the 10 to the negative m factorial, I'm going to have a what? I'm going to have a 10. Right? A 10 to the power of 0, right? And so the other terms are safely bounded, right? So then I have a bounded series, so it's going to be bounded by a constant c, right? Or another constant c tilde over here, okay? So of course, that's going to be a constant c. I can say some number like 100 or whatever. You can say 100 if you want, okay? Less than or equal to this number, less than or equal to that. So some huge constant over here. Good? Okay. And so now what's happening over here? So now what I have is the following. So now this, of course, if I clear it, says that c is less than or equal to this humongous constant over here is just 100 times 10 to the negative m plus 1 factorial times, and this is going to be the numerator now, 10 to the m factorial times n. This is equal to what? This is equal to 100. Now everything is a common factor of what? Everything is a common factor of m factorial. So I'm going to pull out an m factorial over here, an m factorial. And then what's left over here is a negative m plus 1, negative m minus 1, and over here is what's left is an n, okay? So we've just shown that c is less than or equal to that positive constant c is less than or equal to this number 100 times what? Times 10 to the m factorial, and then I'm going to have a n minus 1 minus m. Now remember, n is fixed, so this n over here is fixed. That's fixed. And so now as m tends to infinity, eventually this m is going to be larger than n, so this whole expression is going to be negative. So I have 10 to the negative something, so as m goes to infinity, this expression tends to 0. So we've just proven that 0 is strictly less than 0, which is a contradiction, which means that this number over here, L, which is a solution, this number L could not have been a solution to this polynomial equation. So that shows that L is a transcendental number. Now this is one of the easier proofs of transcendental numbers. In further videos we'll show that E and pi are transcendental, but this gives us a good sense of how we go about proving things are transcendental using this Liouville approximation for algebraic numbers. Thank you very much.